All right, so we have our first two kinematic formulas here, and in this video we're going to derive the next two, which is just going to be using our first two, and then we'll kind of justify, or kind of motivate rather, afterwards why they're useful, why we needed to do that, to get these equations of motions in the ways that we did. So, to get our fourth equation of motion, we're just going to take the first one, this value for v that we have, and we're going to substitute it in to our second equation. And that's going to look something like this. So my second equation is x equals x naught plus 1/2 times v naught plus, but now instead of v, our final velocity in some situation, we're going to plug in v naught. So this is going to be we're going to plug in v. So for this v right here, we're going to substitute in this expression. So this is going to be v naught plus at, all times t. And now we're just going to simplify a little bit. And I'm going to use the same color now. I'm going to switch to green. So this is going to be x equals x naught plus 1/2 times. Now, we have two v naughts here, so I'm just going to write that as 2v naught plus at times t, okay? And so then we're going to distribute our 1/2 and our t. So this is going to be x equals x naught plus, so here, the 2 and the 2 are going to cancel. And then I got to multiply in my t, so I'm just going to get v naught times t. And then over on the right, I'm going to get a times t, so that's going to be at squared. And then to distribute this half, I'm going to get at squared over 2. So plus at squared over 2. And we're done. We're done with the third kinematic. This is our third kinematic equation, or kinematic formula. And so you say, well, we've already got an expression for our final position. We had it in the second one. But this one is different in the fact that it does not contain the final velocity. So if we don't know the final velocity, but we do know the position and some other things, then we can use this expression. And we'll go into a little bit more detail about that in a minute. So first, let's get the other one. So this is our third one. For our fourth and final kinematic equation, we're going to do a very similar thing. So we're going to start with our first equation again, except this time we're going to solve for t in our first equation. So from my first equation, I can subtract v naught from both sides. So v minus v naught equals at. And then I can divide by t. So I get v minus v naught, divide by a, over a equals t. And so we're going to take this, and we're going to substitute this expression for t into, again, our second equation here. So let me start to rewrite our second equation. So x equals x naught plus 1/2 v naught plus v, and now instead of t, we're going to write this expression times v minus v naught over a. All right, there we go. Now let's simplify it. And what color will I use this time? Let's use purple. So let's start to simplify this. So we have, draw a little dividing line, x equals x naught plus. Now, this 1/2 and this a, we can just write as 1 over 2a, so that takes care of that. But then what is this v naught plus v and v minus v naught? Well, this is just the difference of two squares. I can rewrite this term as v plus v naught, and I can do that just because it's addition, and addition commutes. I can write that however, in whichever order I want. And then I have v plus v naught times v minus v naught. That's just the factored form of the difference of two squares. So I can rewrite that as v squared minus v naught squared. And so now I have this expression, and what I want to do is to solve for v squared, just to write it in kind of the standard form that you might see written in a textbook. So I'm going to subtract x naught from both sides. So x minus x naught equals 1 over 2a times v squared minus v naught squared. And then I want to multiply both sides by 2a. So I get 2a times x minus x naught equals v squared minus v naught squared, just our initial velocity squared. And then I'm going to add our initial velocity squared to both sides. And then I'm going to rearrange a little bit. So I get v squared equals v naught squared plus 2a times x minus x naught. And there we have it. There's our fourth and final kinematic equation. So now we want to look at why it's useful to have all four of these. So in all of the last videos, we've been talking about four main variables, if you will. So four main variables, and those variables have been the position of something, something's velocity, its acceleration, and the time interval that's passed. These are the four components that have made up the bulk of the last several videos. So let's look at these four equations while focusing on those four variables. Well, if we look at equation 1 here, it contains the final velocity, it contains the acceleration, it contains the time, but it does not contain the final position. So if we don't know the final position, maybe we can use this equation to solve for something else. Because normally in a problem, what's going to happen is you may be given or you may be able to compute two of these four. And so then you have to pick and find one of these four equations that contains the two things you were given and the one thing you weren't given. And we'll do plenty of examples and kind of work through how to use these. So what about the second one? The second equation, let's see what it contains. Well, it contains the final position, it contains the final velocity, it does not contain the acceleration, but it does contain the time. So it contains x, v, t, but not our acceleration. All right, so that's why that one is useful. And you can kind of see with the pattern here what's happening. And so let's look at the third one. Well, the third one contains position. It contains the initial velocity, but it does not contain the final velocity. And then it contains a and t. But again, it does not contain the final velocity. And finally, for this fourth one, this one does contain position, it does contain velocity, it does contain acceleration, but it is missing t. So not t, I want there. So not t. So these four equations express a relationship between three variables. All of them express a relationship between three variables and exclude the other one. So if we can pick and choose these equations to use in a problem based on what information we have and what information we're missing.